So, in the last lecture we looked at how the earth started warming from the last ice age 20,000 years ago to today. Okay. There were many components to this climate change. The first one is the role played by melting of ice, change in albedo, increase in greenhouse gases like carbon dioxide, methane and water vapor, and the combined warming effect is seen in this temporal variation here, shown here. And so, this is the contribution from gases and melting of ice. Now, this warming was, if you see on the spatial pattern, warming everywhere. Okay. But there is also another component driven by change in ocean circulation. Okay. And the ocean circulation changes were driven by Atlantic meridional ocean circulation, which, as you remember, went through rapid changes during the Birling Aneroid and Younger Dryas events. Okay. And that is shown here in this shaded figure here. Okay. So, and also you must remember, in addition to the changes in ocean circulation and greenhouse gases and melting of ice, there was also increase in incoming radiation from around 150 watts a meter squared to around 160 watts a meter squared, and also the duration of summer changed. Okay. Insolation changed from 450 to 525, well, the duration of summer changed from 145 days to 160 days. So, this also contributed to the warming as well as cooling. So, the total transition that occurred from the last ice age to today, consisting of the role of greenhouse gases, role of melting of ice, changes in ocean circulation and changes in incoming solar radiation in the polar regions. So, all these combined effect can be understood only if you look at the proxy data as well as the model simulation. All this has been combined here, because proxy data are not available at all times. There are periods when there is no data available. The model gives you continuous data, but the model is not perfect. Model has its limitations. So, you combine the model and the observation, and that is called analysis. Analysis is the fusion of the model data, which is continuous in time and space, and proxy data, which is discontinuous in space and time, but is the true observation. So, we need to combine these two to understand what is going on, and that has been achieved by this in this paper. Okay. So, what I described to you is given in the figure caption here in great detail, which you can look at. Now, I will talk about this period which was simulated by the NCAR model under the simulation called TRACE 21K. Okay. And so, this was a coupled model in which the land had 3.75 degree resolution, latitude, longitude, and the parallel ocean model, which had resolution of around 1 degree. Okay. Now, in these transient simulations, the orbital terms are varied, greenhouse gases were varied, ice sheets were varied, and melt water fluxes were introduced occasionally from the sea level rise data. We know how much melt water came into this ocean. Now, all these are put together in the full simulation, but the advantage of running a climate model, you can also run separate simulations. For example, there is one simulation in which only orbit was changed. The other simulation was in which only greenhouse gases were changed, CO2 and methane. The third one in which the ice sheet was changed. and the last one only the melt water fluxes were changed. The idea of doing this individual simulation in which only one quantity is varied is to understand what was the effect of these four forcings on the total change. So, if you change one at a time, you get a better idea of what each one is contributing. Finally, you change all of them together and you get the total change. Okay. So, this simulation reproduces the key features of the climate change that occurred in the last 21,000 years. Okay. Now, let me just remind you what all changes occurred. The solar radiation changed from 450 watts a meter squared to 480 around 11,000 years ago, and then started going down. Okay. So, right now we are in a phase where the incoming solar radiation is declining. Okay. Now, in this period, the carbon dioxide increased from around 180 parts per million 21,000 years ago. As the warming occurred, it rapidly increased to around 240, and finally it increased to 280. In the last 100 years, of course, it has jumped beyond 400 parts per million. And at the same time, the ice sheet, which covered more than 20 million square kilometer area 20,000 years ago, gradually declined, and finally the area came to close to 1 million square kilometer today. Okay. So, all these changes occurred simultaneously, and they all contributed to the warming of the earth. But in this simulation, they did one simulation when everything was changed, and then simulation which only one of these changed at a time, to understand how much contribution is coming from each one of these changes. Okay. So, here is now a comparison. Look at the black. Black is the simulation with all the forcing combined. So, temperature was around minus 4.5 degrees below the present. It gradually increased the global mean temperature, and then it slowly increased to the present state. Okay. That is a black line. Now, this black line is being compared with the blue line, the light blue and the dark blue, which are proxy data obtained from ice cores and ocean cores. Okay. Now, notice that the two do not agree. Okay. The Shakun et al. Data shows about half a degree higher temperature than the model data, and the Marquardt et al. Data, which is only for the last 12,000 years, shows about 1 degree warmer than the simulation. Now, the question is, why is there a difference? So, remember, in the case of model, when you calculate annual mean temperature, we take average of all grid points for which we have data available in the model. But when you look at the proxy data like Shakun or Marquardt, they can only average over points where those measurements were weighed. And if you recall, those measurements do not cover all parts of the earth. Okay. We looked at it in the last class, I will show it again. Notice that this is the area where Shakun had proxy data. So, when Shakun averages over these ice core and ocean core data, his global mean will not be same as that obtained from climate model, where we have data everywhere. So, we need to see how we can understand the difference between model and observation from proxy data due to a different way of averaging. Okay. So, what the model people did was, the black line corresponds to all the grids in the model, every grid point in the model. Then this light green is where they only averaged over where proxy data was present in the observation. So, you do only proxy data, annual mean temperature, then you get a slightly higher value. Okay. So, this shows that the calculation of the annual mean is sensitive to the location of the proxy data. Proxy data is not there in all the places, only there in some places. So, when you calculate global mean temperature from proxy data, you will make errors, and that error is given by difference between the light green line and the black line. Okay. The thin lines are the model simulation, individual simulations, while the black line is the ensemble mean, average of all simulations. Okay. Now, to understand the difference between the model simulation based on only where proxy data is there and the Shakun data, what the model people did was, instead of taking the annual mean, okay, you only take a seasonal mean, because the proxy data from which we get temperature is based on the abundance of certain animal species. Okay. And these abundance of this species depends on temperature. Now, it is assumed that it depends on annual mean temperature, but unfortunately some species, their abundance is sensitive to the seasonal maximum temperature in that region, not annual mean. Okay. For example, summer. In summer temperatures are higher, some species will be more abundant. Okay. So, what these model people did was, they average over the site data, but only average over the summer period, okay, not annual mean. This is called biased averaging, and when you see, then it suddenly jumps to a value close to both Shakun and Marquardt. So, clearly shows that when you deal with proxy data, you need to be very careful. Proxy data is not available everywhere around the globe. So, calculating global mean involves some errors, plus proxy data may not reveal to you the annual temperature, it may be revealing you the temperature in summer or in winter, depending on the proxy. So, this comparison between model and observation clearly shows that one cannot rely only on proxy data, because proxy data is available only in certain locations, not the whole globe, and secondly, proxy data may not tell you the annual mean, may be telling you what is happening in a given season. Okay. So, this comparison between trace simulations and proxy data clearly shows that there are problems with proxy data, and of course, there are problems with model data also, because model does not take into account all processes that occur in reality. But still, one can say that the agreement between model and the proxy, if properly averaged, is within about 0.25 degrees, which is quite good, okay, because 0.25 degree accuracy in global mean is substantially great achievement. Okay. There is also an insert here shows there are more variations on a scale close to the present, the last 2000 years, which is shown as a blown up figure here, and there you can see there is a big difference between model which simulates only the seasonal temperature and one which does the annual mean. Interestingly, this period where there has been a cooling over the last 1000 years, as obtained from Marquardt data, is reproduced by model, okay, the cooling. So, there are differences during the last 2000 years, which is different from the last 20,000 years. So, what I discuss here is given in words here, and in these papers they not only compared the trace simulation, they also took simulation from another model called FAMOUS and a third called LOWCLIMB. Because you cannot rely only on one simulation, one model, people look at many models, because each model is a different representation of the physics. So, when you look at all of them together, it gives you confidence. So, here is that comparison. So, here you see three different models: CCSM3, which was used in trace, LOWCLIMB another model, and FAMOUS another model. And when they include all the forcing, you get the black line, okay? That is including all the forcing. Then they do individual forcing. For example, only greenhouse gases. When it is simulated, trace shows much less warming, showing that greenhouse gas alone cannot explain the warming we saw from 10,000 years ago to the present. Okay. For that, you have to include the variation in the orbit, changes in ice cover, and changes in meltwater forcing. Okay. Only when you put this 3 along with greenhouse gas, you get the black line, okay, the all simulation. But if you just add these 4, you get this gray line, showing that when these 4 changes are put together, there are feedbacks in the system which is not sum of these 4. Okay. So, this shows system is not linear. The system was linear when you did simulation with each one of these forcings and added them together, you should get the black line, but we are not getting it, clearly demonstrating that there are feedbacks, as I have put here. The role of feedbacks is very important. So, that has changed the warming in the last 10,000 years. This is with trace simulation. Now, we look at LOWCLIMB and FAMOUS, you see that the way they simulate the role of greenhouse gases is different from the way it was done by trace. Okay. So, trace simulation is somewhat superior to that by LOWCLIMB and FAMOUS. So, I would consider the CCSM3 simulation to be a more realistic simulation than LOWCLIMB or FAMOUS models. Okay. But all of them show that if you only, for example, choose ice or only orbit, there is hardly any change. If you use only ice, there is some change. If you use only greenhouse gas, there is some change. When you add all the 3, you get the black line, which is not same as when all of them are put together in the model. Okay. So, this kind of comparison is very important, because it highlights that among the changes, the greenhouse gas is the most prominent. Okay. Next comes the orbit, next is ice, and the meltwater forcing, although very important during the Younger Dryas and other rapid changes that occurred, but is not important in the last 10,000 years. Okay. So, the meltwater forcing was important from 20,000 to 10,000, but not in the last 10,000. And you see that the same thing is true for ice. Ice changes were very important in the phase when the deglacial phase, but in the Holocene, ice is not as important as greenhouse gases. Now, you can see this greenhouse gas increase was in response to the temperature change of the Antarctic as well as the global mean, but there is a question about why did greenhouse gas change in the last 6,000 years. Okay. Now, this is not completely understood. I will talk about this after I finish this discussion. There are two views. One is that carbon dioxide continues to increase after the ice sheets completely retreated because of the changes in the carbon cycle and the methane cycle. But the alternate view, which I will discuss soon, is by Professor Rudiman, whose book you are using in this course. Rudiman claims that what happened in the last 6,000 years is on account of human beings. He claims that human beings, as the population exploded in the Holocene, they increased the area under agriculture, and that increased the methane emissions. And so this is a controversial hypothesis. Not everyone agrees with it, because we do not have accurate data on how the human population increased and how the land used for agriculture by cutting out the forest, how the change in time is still a guesswork. Okay. Now, you must remember that when you use proxy data, we convert the data obtained from various depth to the age. Now, this conversion is not perfect. It is done in certain periods for which we have the dating using radioactive decay of some species like uranium or carbon or others, but they are done only for a few locations, few depths. Okay. In between you are interpolating. So, there are errors in terms of converting depth to age. Okay. So, various kinds of techniques are shown here. So, you must remember that when you look at proxy data, the time that is given there has an error of at least 1000 years. Okay. So, you should not take that data to be the truth, okay, because it is not like taking temperature over the last 150 years when we know at what time we took the temperature. When you go to proxy data, you are depending on deposits either of the ice or of the ocean core, and you are inferring at what time that deposit occurred by very indirect means. Okay. So, there is a scope for error, and so whenever you look at proxy data, you need to be very careful about the fact that the time is not precisely known. Now, I am saying this because today all this data is available from various websites. You can download the carbon dioxide data, temperature data from various proxy, various websites. There are people who take this data, do all kinds of very sophisticated statistical techniques to get results without knowing that these data have errors. So, a lot of papers have been published where the people were mathematicians and statisticians who did not realize that the data that is given to them has an error bar of 100, 500, 1000 years. So, you are very careful when you use powerful techniques of AI and machine learning to look at proxy data of the last 20,000 years. You have to fully be aware of the errors in this data. Okay. Now, this discussion about the global temperature obtained, for example, with tropical winter magnesium calcium ratio basis, there is a bias in that, or if you use alkanone as your source, it has also a bias both in the tropics and mid latitudes. So, here they are showing how the global mean temperature varies depending on which proxy you used. Okay. So, each proxy has its own problem, and if you correct for it, then you get a different value, and the errors can be as high as 0.75 degrees Kelvin about 9000 years ago. Okay. But notice that in the last 3000 years the errors disappear, because we have much better proxy reconstruction using tree rings. If you use tree ring, you have much more control over the biases that are there, because the tree ring growth depends only on temperature primarily. Okay. But other sources of proxy data from ocean cores, they depend on the abundance of certain species, and that species may only sample the summer or the winter temperature. So you cannot infer annual mean from there. Okay. So these are issues you should be aware of. Okay. Now, so here in the supplementary data of the Shakun et al. Paper in Nature, they discuss the global mean temperature obtained deriving by perturbing the proxy records, because there are errors in the proxy record. So you put that error into your estimate, and you can see that in certain periods the errors can be of the order of half a degree. The same data, you do slight perturbation of the proxy data, you get a half a degree variation. Okay. Note that that error is not that much in the last 7th or 10,000 years, but it is more in the period where younger dryas occurred, okay, when there are sudden changes occurring. Okay. So, and on this side you see on the right hand graph the error in temperature to age, date of the model timing, as well as proxy estimation. Errors are each one of them typically of the order of 0.1 to 0.2 degrees. This is due to the proxy conversion temperature. This is due to age model errors, and these errors are large in the past compared to the more recent period. And when you combine, some errors get reduced and you get this result when you combine both. Okay. So all these factors Shakun and others considered, and that is why I consider that paper to be a landmark paper, because not only they combined all the proxy data, they also looked very carefully into the errors introduced by the conversion of proxy data abundance to temperature, as well as the age of that proxy. Okay. So this a lot of people do not understand, and so this particular paper is a landmark only because they went thoroughly into all the possible errors in the proxy data due to conversion of abundance of some species to temperature and the age of the proxy. Now remember, there are total of 80 records in Shakun et al.'s paper, and they have put that in red when they took all the 80 into account. But not all the record had data every 200 years, some of them have data every 500 years, 1000 years. So if you only consider those records whose resolution is very good, 200 years and less, you get the blue line. Okay. So you want to take more number of proxy data to represent the global mean, but when doing that you cause an error in the time resolution. Okay. So they analyze the difference between taking all the 80 and only those 39 with a higher resolution. They saw that it was okay in this period, they agreed, and but there is some error of the order of half a degree around the last calibration maximum, and error of about again half a degree during the younger dryas cooling. Okay. So these are things one must be clear about, because these are there. Then they use what is called jackknifing method, which is you take the proxy data, okay, and randomly exclude 50% of the data and do the averaging again. Okay. So you do not only choose what you like, you take the full 80 data, throw 40 out at random, take 40 and do it many times. And today with availability of Monte Carlo techniques and computer power, you can do it thousands of times, and then you get the mean and the standard deviation. Okay. So that shows how much variation occurs on account of the errors in the proxy data, and again you can see that errors can be order of plus or minus half a degree. Okay. So, this all I am showing you from the Shogun et al. Paper to convince you about how thorough their analysis was in combining 80 different core data, different proxies, different time resolutions, different errors in age determination. So, they looked at all the issues very closely. Okay. So, this is given in detail here from their figure caption. You can look at it very closely. So, this is a jackknife test in which you take only 20 data or 25 data or 30 data and calculate global mean temperature. So, here is when all the 35 data are taken and you reduce the number of data points, you can see that the global mean temperature difference are large in this time period. Okay. But when you come close to the present time, of course, errors are small. Now, here is a comparison between the last glacial maximum and the last 100 years, how the spatial differences in temperature of the atmosphere at the at 1 meter height. Okay. Now, this shows that last glacial maximum was colder by around 25 degrees around this Siberian region and also Greenland. You can see that they were very cold because of thick ice sheets, but the tropics were only colder by 2 to 3 degrees. So, this is a huge variation between the tropics and the northern polar region as regards the surface at temperature. So, this clearly demonstrates the role of ice albedo feedback. In a place like India, there is not much impact of ice albedo feedback, while in northern Siberia and Greenland, ice melting resulted in very high absorption of solar radiation by the meltwater. So, the warming that occurred from LGM to today was as high as 20 degrees. Okay. So, I want you to remember this big difference between tropics and polar regions. So, right now, for example, the tropics are warmed by 1 to 1.5 degree, but the Arctic is warmed by 4 degrees. Okay. So, this is why global mean temperature warming at 2 degrees is very serious, because 2 degrees in global mean means the Arctic region would have warmed by 10 degrees, and these are large changes and it will introduce all kinds of perturbations which we will talk about later. For example, there is a lot of permafrost, that is frozen soil containing methane in Siberia. Okay. So, if Siberia warms by 10 degrees in the next 100 years, huge amount of methane which is stored in this permafrost will come out. Okay, and will have huge impact on the global mean temperature. That is why we must understand that when the temperature warms, the warming is not uniform. Okay. Warming is less in the tropics and more in mid latitudes. Okay. And there is one more example showing what I discussed earlier, showing how the model output difference is there depending on whether you do the annual mean or seasonal mean in comparison to proxy data. This we have discussed already. This shows that proxy may not represent the annual mean. Okay. And here you come back to the original figure of Shakun, and I will continue this discussion in the next lecture. So, in the next class we will continue discussion about how the temperature of the earth changed from the last glacial maximum to today.